Hi everyone, let us discuss inverse function theorem. Okay, so let us try to understand the meaning of statement of inverse function theorem and then we will discuss its proof. What will I do? I will draw the diagram simultaneously so we can easily visualize the meaning of this inverse function theorem. Okay, so what we have, I and j be two open intervals in R. So what I am going to do, I am going to consider two intervals. This is interval I and this is interval j. Both are open intervals in R. F is a function from I to j. Okay, we have a function f from where to where? I to j. And there is some point x naught in I and its image is y naught here. F of x naught is equal to y naught, right? The given important thing is function f is differentiable at x naught. Point number 4, function f is differentiable at x naught and its derivative is non-zero. This is another important thing. F dash of x naught is not equal to 0. Then theorem says there exists an inverse function f inverse. So as f from I to j, you can easily see f inverse will be from j to I. F inverse will be from j to I such that it is differentiable at y naught. If function f is differentiable at x naught and its image is y naught, then function f inverse is differentiable at y naught and its derivative can be obtained in this way. Derivative of f inverse at y naught is equal to 1 upon derivative of f at x naught. This thing we have to prove. So what will I do? I will write all given information one by one. Okay, so we will start its proof from here. Just a minute. Yes. So what we have, I will write a first important thing. We have f is differentiable at x naught. So you are familiar with the definition of differentiable function. Simply I will apply the definition. Definition says differentiable at x naught, therefore limit x tends to x naught f of x minus f of x naught divided by x minus x naught. This limit exists and that is nothing but derivative of f at x naught. This is a very important thing, so that's why I am calling it as equation number 1, right? The second important thing is function f is bijective. We have f from I to j is bijective. Bijective means what? 1, 1 and on 2. So you know that if function is bijective, its inverse also exists. So let me mention here, implies f inverse from j to I exist. Okay, so f inverse exists, and the second important thing is that its function is bijective, that means on 2. So that's why, and for any y belongs to j. So if you take any point of y, in j, there exists some point x in I such that f of x is equal to y. Since the function is bijective, there exists x belongs to I such that f of x is equal to y. This is a very important thing I wrote here, right? So function is onto this, so that's why I wrote. So let us focus on what we have to prove. So here we have to prove that function f inverse is differentiable at y naught. Okay, so we have to prove that this function f inverse is differentiable at y naught. Again, using the same definition, I am going to prove it, right? So let us consider. Will you tell me what we have to consider here? When we have f is differentiable, we use this definition. Same definition I am going to use to prove f inverse is differentiable. So consider limit y tends to y naught, I suppose to write. See, when we talk about f, it's in domain, it has 2 point x and x naught. X is moving towards x naught. But when we talking about f inverse, so its domain is this j. So it has 2 points y and y naught, and y is moving towards y naught. So that's why I should write limit y tends to y naught f of y minus f of y naught divided by y minus y naught. So this is equal to limit y tends to y naught, that means f inverse of y tends to f inverse of y naught. Okay, so maybe you will get confused. How could I write this? Y tends to y naught, that f inverse of y tends to f inverse of y naught. So let me write a reason here. How could we write it? What we have, f is differentiable. What we have, f is differentiable. We know that every differentiable function is continuous, so that's why f is continuous. Differentiable at x naught. Okay, so f is continuous at x naught. Since we know the result, every differentiable function is continuous. As f is continuous at x naught, f inverse will be continuous at y naught. So implies f inverse is continuous at y naught. Okay, so there is one result. As y tends to y naught, and if f inverse is continuous, you can write f inverse of y tends to f inverse of y naught. Okay, so sequential criteria of continuity, with the help of that I could write it, right? So that's why as y tends to y naught, I could write f inverse of y tends to f inverse of y naught. So let me do the same thing here. So f of, what is our y? Our y is f of x, right? Minus f of y naught, f of y naught, f of y naught. But see our y naught, see I should write here f inverse, since we have to prove the function f inverse is differentiable, right? So y naught is nothing but f of x naught, so I should write here f of x naught, f of x naught. There is f inverse, so I should write f inverse here, divided by y means f of x and y naught means f of x naught. Understood? Now by mistake I had written here f only, but actually we are proving that f inverse is differentiable, so that's why I supposed to write f inverse everywhere. So but y is equal to f of x, that's why I wrote f of x here. Y naught is equal to f of x naught, that's why I wrote f of x naught here. Will you guess the next step? Okay, just a minute, there is no more space to write. Let me clear it, make a screenshot of it, then we will go further. Okay, so this space will be enough to prove remaining part. So this is equal to limit. So you know that as f of x is equal to y, x is equal to f inverse y. So that's why f inverse of y is nothing but x. Similarly, f inverse of y naught is nothing but x naught. See, f is a bijective function. F and f inverse will get cancelled. We will have x only minus. What will happen here? Here also same thing will happen. F and f inverse cancel. X naught divided by f of x minus f of x naught. So this is equal to limit x tends to x naught. See, it is at numerator, so you know that if you have any term at numerator, you can write that term is in denominator of denominator. I will do the same. So f of x minus f of x naught, I am shifting at denominator of denominator, we will have it here. Okay, so let us apply the limit. At numerator we will have 1 only. If you apply the limit, from equation number 1, its value is f dash of x naught. So that's why we can write this is nothing but f dash of x naught. Yes, a derivative exists, right? So yeah, so therefore we say that f inverse is differentiable at y naught. We proved it, and its derivative, and let me write its derivative at y naught. What we have got? We have got its derivative is nothing but this one. So this is 1 upon f dash of x naught. So in this way we proved this theorem. Make a screenshot of it, then we will stop. Thank you. Bye bye.